Hello everyone, welcome to CS for All. Today we are going to talk about theoretical analysis of space and time complexities. So what I am implying to is the Big O notation, the very famous Big O notation. So Big O notation is a very important topic. So without wasting any more time, let's roll the intro. So now you might ask, what is a Big O notation? So Big O notation is basically a mathematical notation which helps us to understand time and space complexities, or which helps us to represent the time and space complexities. So let's say we have an algorithm where time is a function of, let's say t is the time, and it is a function of an square plus bn plus c. Fine. So we have this algorithm where time is a function of an square plus bn plus c. So time follows a quadratic curve of this form. Now the question is, how are we going to represent this entire expression in the form of a Big O notation? So basically we will be writing a big O here, and then we will be eliminating all the constants. So what are the constants present in this expression? The constants are a, the constants are b, and finally the c. These are all the constants, so we are going to eliminate them. So let's eliminate them. And now we are only concerned about the value of n, because time will shoot when the value of n will change. So we are concerned about the highest power of n. So I can see two values of n here. One is n square and other is n. So basically I will be taking the highest value or highest power of n. So it will be n square. So the following expression in Big O notation will be Big O of n square. That is a quadratic function. So if we plot a time versus input data graph, so basically this is my time versus input data, that is n graph. This would be the Big O of n square curve, right? So this is a quadratic curve, and the previous expression which we had, that is Big O of an square plus bn plus c, right? So this will be the curve for the previous expression. Now what I want to say is a of n square plus b of n plus c would always be less than or equal to some constant k into the n square which we have here. So whatever is the value of a or value of b or n or c here, this will always be less than or equal to some constant k into n square. Now we will be looking into this particular time versus input graph, and we will be talking about all the time complexities and giving some examples of each one of them. So talking about this fine line here, this is Big O of 1. So in the previous video we talked about this particular time complexities. So if you have a sorted array, so the array is sorted in ascending order, and you want to find the maximum element from the sorted array, so you will be basically taking out the last element, because if the last element will be the maximum element present in a sorted array which is sorted in an ascending order. Now let's talk about this log of n complexity. So basically log of n complexity is a very good complexity. So we use this in binary search. We use binary search when we see a range of numbers which is arranged monotonically, that is they are increasing in a monotonic fashion. So this is a very good time complexity. It grows slowly with time. Then we have this O of n time complexity. So it is considered a good time complexity. That is, it is slower than the log n complexity, but it is a good time complexity. Then we have this n log n time complexity. So basically if you are sorting a range of elements in an array or vector, you can use the inbuilt STL sort function, and that is basically an ideal merge sort, and that will cost you a n log n time complexity. So that is an example of n log n time complexity. Then we have the basic O of n squared time complexity. It is a bad time complexity. In order to give an example of this n squared time complexity, I will be making use of a problem. So suppose you have to print this pattern, right? Let's say you have 5 rows and 5 columns. Okay, so you have 5 rows and 5 columns for this pattern. So n would be 5 here, and you have to print all the stars, right? So you will be making use of 2 for loops, each running from 1 to 5, right? So this will basically take you a O of n squared time complexity. So this is an example of O of n squared time complexity. This is a quadratic function again. Now, if we want to talk about bigger time complexities, yes, we have those. So that would be O of n cube, or maybe O of n to the power 4, or maybe an exponential time complexity of O of 2 to the power n. So basically, if we want to print the subsets, then we have the time complexity of big O of 2 to the power n. Now we will write all the time complexities of algorithms and compare them throughout. So first we have the O of 1 time complexity. This is the best time complexity we can have out there. Then at the very end we have O of 2 to the power n. That is, if we have an array and we want to print subsets of the array, then we will have a 2 to the power n time complexity. Before this, we may have a big O of n cube or n to the power 4. Before this, we can have n squared time complexity, that is a quadratic time complexity. Before this, we can have a n log n time complexity. And then before that, we can have a big O of n time complexity. And before this, we can have, a big O of log n time complexity. That is, if we are doing a binary search, right? So suppose in the interview or during CP, your time complexity of the problem or the solution is 2 to the power n. Now the interviewer wants you to optimize it further. So you have to bring the time complexity from here to here. Now again, the interviewer wants to optimize it. You have to bring it to here, then to here, and maybe finally up to here, right? So you can do the optimization by using a data structure or maybe a technique of searching or sorting. So when we will be learning about the data structures, we will also know how to reduce the complexity of problems by using those data structures and algorithms. Moving forward from the next videos, we will be learning about theoretical analysis. So we will analyze loop-based codes, bubble sort, merge sort, then searching functions such as binary search, factorials, polynomial evaluation, and then the Fibonacci series. So that's it for today's video. I hope you really enjoyed this video. If you have any doubts or queries, you can write down below in the comment section, and you can directly reach out to us through LinkedIn. So stay tuned till the next video. Till then, stay happy, stay healthy. Bye.
It's my life, it's now or never. But I ain't gonna